All right, so welcome back. Here's the last section, 3.2, photoelectric effect. And here the main idea is you have an energy source, essentially emitting light, radiation. It's going to travel with a certain frequency. So the higher the energy, the higher the frequency, and the smaller the wavelength for individual waves that you're going to see there. So what I've done already here is kind of represented some of that information. So we've got an energy source up top. It's emitting its energy, and eventually it's going to strike matter. And it's at this point of contact, or this impact point, that I'm going to talk about here, because at that point of impact something important is happening. So let me just circle it yellow. And so this is what's happening here at the point of impact. At the point of impact, you're going to see that the atom, the specific atom or the specific atoms, because obviously you can't isolate just the one photon that's coming in. There's a whole bunch of them traveling. And so when that photon strikes, if we just take the perspective of an individual photon striking an individual atom, that's kind of what I've depicted here, then we can actually talk about what's happening within that one singular atom, but it would be true of all the other atoms being impacted. So at that point of impact, the atom that's impacted essentially we'll have, if I draw the atom here, let's just draw one here with two orbits. Say we've got this one, we've got that one. And just like we saw in the previous sections with the spectroscopy section and whatnot, when we're talking about ionization energy, it's kind of what's happening here, except the electron is not going to be removed. That electron that's orbiting the proton core is not going to be removed. So I'm just going to represent the proton core with a positive. And here the incident light is coming in, and it's, let's say it's striking that particular electron. So this specific electron then is going to go from the relaxed state, which is currently at, and it will probably absorb all that energy. Not probably, it will absorb the energy. And when it does, it'll begin to vibrate, and it'll go to a higher energy orbital. Now, I didn't draw more than two, but theoretically, it could go from this energy state, it could go up to a higher energy state. And so this, in this case here, this position up here would be the excited state. And this one here, just to compare, this is the relaxed state of that electron that I'm referring to. So when the electron goes from the excited, from the relaxed state, it'll absorb the energy, and then it'll make its way over to the excited state. And as it goes to that higher energy level, then all that energy is absorbed, but when that electron then goes back down to the relaxed state, what's going to happen is that energy is going to get released. So it absorbs it on the way to the excited state. And let's go and represent that in a different color. When it comes back down to the relaxed, here this is going to be a release of energy. Now, where is that represented? In the diagram that I have up above. And so once it strikes the matter, and that electron goes from excited to relaxed to excited, and then on the way back down, that energy is going to be released. And so let's go ahead and depict that in purple here. So it'll be released. And I didn't do a good job, so let me just represent it as it should. It's going to be a wave. And when it goes through, the main thing about the photoelectric effect is what color do we see? So if I represent just a generic eyeball here, let's go ahead and represent that as, I guess, in yellow here. We've got the eyeball here. And the main thing is, as when the light comes in, the light then is going to be attached, obviously, to a processing center. That's your brain. And so that brain will then interpret the frequency, because it's really the frequency that we're interested in here, this frequency of the emitted, or the frequency of the released, as opposed to the frequency of the source here. It'll be very similar to the frequency of the source when it comes out. So this frequency here will be very similar to that. And that's the the frequency that the brain's going to interpret. Now, obviously here, frequency is proportional to energy. So when the frequency comes in, it'll have a certain amount of energy. Now, that's important because once it goes through here, the brain is going to interpret that frequency. And essentially, it's going to give you a conclusion that's going to be in the Roy G. Biv category. In other words, it's going to be at a very specific color. So what you need to be able to do for this particular section is just understand the math that's involved. There's a couple equations you need to know about. So let's kind of go look over those equations. I'll make some space here, and then we'll go quickly to see what that means. So let me move these over here to the right. Let's put this over here. And so what I'm referring to here is that when the frequency comes in, you got to pay attention to two major equations. So those equations that you got to be aware of are the speed of light equation, which is c, the speed of light, is equal to the wavelength times the frequency. Now this frequency variable can be represented in two ways. So this is the way that I would remember, just because f, frequency. But I think if you look at the packet on the AP exam and other materials, you're going to see that represented not with an f, but rather you're going to see this represented as c is equal to the wavelength times this variable here. So just make sure that you understand that these two things here, these are the same, which is equal to frequency. Okay, that's important to know there. The other equation that you need to be aware of is going to be the energy equation, and that is the energy of a wave is going to be equal to Planck's constant, that's represented by a letter h, and that's going to be multiplied by the frequency. Now, since both of these equations have a common variable, frequency, what we can do is we can take these equations and rewrite them and just go ahead and I guess reformulate or derive the equation for frequency on both. So I'll do the energy here on this side. I'll do the speed of light on this side. Let's do the energy first since it's further to the left. So the frequency is going to be equal to energy divided by Planck's constant. And for the speed of light, frequency is going to be equal to the speed of light divided by the wavelength. So notice here the two parts. Frequency is the common variable. So if I take the other pieces here, these sections, I can actually combine them and make them equal to each other. And so that would mean that my equation would be E over Planck's constant is equal to the speed of light over wavelength. Now, you could do that. You can also substitute into frequency. So as long as you know the energy and the Planck's constant, you can actually take these two variables here. Instead of isolating them like this, you can actually take this ratio here between energy and Planck's constant, and you can actually plug that in to this equation, and that'll give you a slightly different equation. Now, I'm not going to go ahead and derive that here for you, but you can do that on your own. But what you should know, though, is if I take this equation that I've got at the bottom here, you essentially want to make sure that you understand the relationships between the variables like we did with the gases earlier in the previous section. I think it was 3-4. The thing is, as there's a couple of relationships you need to keep in mind, and so those are the following. So we know that as energy goes up, then that means it's going to be directly proportional to an increase in frequency. And both of these are directly related. So when either one of these goes up, we've got to keep in mind that frequency is going to lead us to have smaller wave sizes. The wavelength goes down, so there's an inverse proportion to the wavelength. And so these relationships here are important for us to consider as you consider some of the problems here on this particular section. Now, there's not much more to discuss beyond that, but once you figure out, say, the energy of something or are able to figure out the frequency, you can always tie it back to the color that is going to be associated with that when you compare that to the electromagnetic spectrum at the very end. So that is 3.12. That'll bring an end to the review, but if you haven't already done so, go ahead and subscribe, keep watching, keep learning, and we'll see you in the next video.